This is an interesting but rather experimental reaction. First we're going to prepare a solution of glyoxylic acid. Then we're going to see if this can react with phenol to produce a substituted mandelic acid. We're starting with 30 grams of oxalic acid dihydrate. We're going to be dissolving this in water, so it's not important to use the dehydrated acid. Just make sure your molar calculations take this into account. Now we add 100 ml of water. Note that this isn't going to be enough to dissolve the acid completely at this stage. And a large magnetic stir bar. Now we weigh out 6 grams of magnesium metal shavings. This is a slight excess in theory to what we need. With the oxalic acid and water mixture stirring, we slowly start to add the magnesium metal. This reacts pretty vigorously with the acidic solution, bubbling and giving off hydrogen gas. There is also quite a lot of heat evolved. Keep adding the magnesium metal, but not too quickly that the reaction gets out of control and too much heat is produced. As the temperature rises, we use an ice bath on the stirring plate to cool the mixture. The last pieces of magnesium take a while to dissolve. The mixture now has a quite strong characteristic aldehyde aroma. After 30 minutes we removed the mixture from the cooling bath and allowed it to warm to room temperature, and then continued stirring for an hour to ensure complete reaction. Next we weighed out 13.4 grams of potassium hydroxide and dissolved this in 20 ml of water to create a solution. Whilst stirring the reaction mixture, we added this potassium hydroxide solution. We think that the idea here is to precipitate a lot of the magnesium as magnesium hydroxide, forming the potassium glyoxylate salt in solution. The result was a very pale yellow mixture with a white precipitate, as you can see here. We filtered this through a glass sinter to remove the precipitate. This was a little slow, but we got there in the end. Next we weighed out 24 grams of solid phenol. Be careful with this stuff, not only does it sting, but it's toxic and causes bad skin burns. And then we weighed out a further 15 grams of potassium hydroxide. And we dissolved this in 70 ml of water to form a solution. Okay, so now we've got a solution of potassium hydroxide and our solid phenol. We're going to dissolve the phenol in the hydroxide. Actually, we did it the other way round. We added the potassium hydroxide solution to the solid phenol and it dissolved. This is now a solution of potassium phenolate in water. Our glyoxylate filtrate has now passed through the sinter. So now we add the potassium phenolate solution we just prepared to this. Here's the result, a rather murky, slightly cream-colored mixture which looks a little bit like an emulsion. We then covered this up with wrap and left for 48 hours to see if any reaction occurred. Here we are after 48 hours. It's hard to tell if this is two layers, a precipitate or an emulsion. To start with, we vacuum filtered this mixture through a glass sinter to remove any solids. Then we tested the pH of the milky colored filtrate in order to check that it was still strongly alkaline. Oops! Well, that's a positive test at least. Now we're going to acidify the mixture using concentrated hydrochloric acid. As we added the acid, some heat was produced, and small globules of unreacted phenol were formed in the mixture. We acidified to a pH of around 3, and then let the mixture settle. The top layer is unreacted phenol, which is always a liquid in the presence of water. We used a pipette to remove the top layer of phenol, and then covered the beaker in plastic wrap and left it in the fridge for 1 week to chill and settle. After a week of chilling, some crystalline precipitate had formed in the mixture at the bottom. So we set up for filtration again. And again, this took a little while to filter off. And we let the crystal dry thoroughly on the pump. Here's what we ended up with. 3.2 grams of a crystalline mystery white solid. It's acidic to indicator paper, but it's entirely possible that this is just the oxalic acid that we started with. We tried testing the solubility in a few different solvents. First, water. It doesn't seem very soluble. It took a whole small beaker just to dissolve the tiny bit of solid. Next up, dichloromethane. And here it's completely insoluble. Now for diethyl ether. Regular mandelic acid is very soluble in ether, but we don't know about the hydroxy version. Doesn't seem to be at all soluble. Finally, sodium hydroxide solution. Here it's a bit more soluble. This is interesting. This solubility behavior isn't consistent with it being oxalic acid, especially because of the low water solubility and the insolubility in ether. But we're not sure exactly what we've got here. We can't find much information about for hydroxymandelic acid. One report says it's white crystals. Another says it's a red powder. If we've obtained this as a product as per the original reference, then it's a 6.5% yield on starting phenol. If anyone has any info, then please let us know. If there's a way to get this reaction to work, then it could be a very useful synthetic route to phenethylamine compounds.